Good morning. Today we're talking about chemical reactions. You remember that chemistry is the study of matter and the changes that matter goes through. And one very important category of those changes are chemical changes, and we call those essentially chemical reactions. And I'm sure that Jen has talked about all different kinds of chemical reactions, and we can broadly categorize them for us into about 5 different groups. You probably have gone through those as well. And so today the idea is to show you an example of those chemical reactions with the emphasis on you trying to record observations. You remember that there are kind of 4 general indicators to chemical change: the evolution of heat and or light, the production of a gas, the formation of a solid precipitate from aqueous solutions, and a general dramatic unexpected color change. So as we go through these 7 chemical reactions, you're going to be looking for those general indicators and recording them on the lab. The lab that you're working with here shows kind of the 4 different categories that we oftentimes put our chemical reactions into. Combination and decomposition reactions are sort of mirror images of each other. In the combination reaction, we always end up with one product. In a decomposition reaction, we always have one reactant. You remember that our reactants are on the left-hand side of the arrow, the products on the right-hand side of the arrow. The arrow itself then is a representation of that chemical change. The other 2 categories here are replacement reactions, where one thing replaces another. Some students find the generic symbolic A, B, C, D nomenclature helpful. Others really do not, but shown here then those general chemical reactions. In the case of a single replacement reaction, one thing gets replaced, and in the case of a double replacement reaction, not surprisingly, 2 things get replaced. The 5th category that I'm sure that Jen has probably talked a little bit about is combustion, that we're not going to do today, but you'll see that at various times during the class. And so off we go. Here then, reaction 1, the combination of sodium iodide in aqueous solution with lead nitrate in aqueous solution, a double replacement reaction. And in this instance, we use a little bit more than the quantities suggested in the lab, just because I want it to be very visible. And in this instance, I'll just add a little bit of deionized water to increase the amount. Deionized water, of course, not going to have any effect on the chemical reaction. Here then comes, there is, in fact, I could pause for a minute, is the aqueous sodium iodide. You might note that nothing is visible. It is a more or less colorless, transparent solution because the sodium and iodide ions have been separated by the action of water and are now sort of in that test tube. Here comes then the other reagent, aqueous lead 2 nitrate, which also is a transparent, colorless solution. And when we combine the 2, we see an immediate chemical reaction. 2 things you might note here. One, of course, that dramatic, unexpected color change. And the second thing that might not be as easy to see in the video is that this new substance is no longer transparent. That is to say, it is opaque to the passage of light. And for us in chemistry, what that means is that there are solid particles in there, very finely divided and suspended in the water, but nevertheless, the formation of a solid, strongly suggested by the lack of transparency of this new substance. If I put my fingers on the bottom of that test tube, I can't detect any real heat being produced, but we do have those 2 general indicators: dramatic color change and the formation of a solid. Moving on here to our second reaction involving the decomposition of copper 2 carbonate. Scoop some out of here. and we'll have a look. It is, as you can see here from the video, a green powder, green solid. And what I'm going to do here then, because decomposition reactions often require energy, that is to say, they are not rapidly spontaneous, I'm going to use heat, as we often do in chemistry, to speed up that chemical reaction. Here using the lab burner and the striker. Students really love that. Maybe you can see the flame, maybe you can't. It's a very, very, very pale blue. Adjust it a little bit. I use my test tube holder here, grabbing my test tube, and you're directed to simply put that copper 2 carbonate in the flame. I'm moving it around a little bit to encourage a little bit of mixing in there. We're watching then the transformation that occurs when the copper 2 carbonate is heated. And if you look carefully there, I don't know whether you can see it, but you can actually watch the solid particles sort of jumping up and down, which is a very interesting phenomenon and suggests strongly that in this decomposition reaction, some gas is being produced, and it is that gas, the evolution of that gas, that is causing those particles to sort of jump up and down. The other, of course, obvious indicator of a chemical reaction is that dramatic color change. Again, you can watch those particles kind of jumping up and down in there from the pale green to obviously a black solid. Again, oftentimes more than one indication of that chemical reaction. I'll put that in there and let that cool down just a little bit, and then maybe later we can dump that out. Reaction number 3, as I recall, is another decomposition reaction. In this case, your old friend, sugar, sucrose, which is a disaccharide. We'll talk more about carbohydrates as an important class of biomolecules. Again, moving over here, since I've got a bad scooper, I'll do this over the sink. Putting then a small scoop of solid sucrose in our test tube. Won't spend a lot of time describing it, since most of you know kind of what table sugar looks like. And then again, because we're trying to accomplish a decomposition reaction, oftentimes energy required to make that happen rapidly. This is a tricky one because I want to decompose the sugar, but I do not want to combust the sugar. And if I heat it too strongly, the sugar will actually burn in oxygen. But what I'm trying to do here is a simple decomposition reaction. If you look at your lab, you'll see the chemical formula for sucrose, C12H22O11, and it is then decomposed into simpler substances. In this case, then, heating it very, very slowly, and of course many of you have already done this chemical reaction in a campfire or something, where you take that sugar and decompose it into simpler substances. One of the general rules of simple inorganic chemistry is that if water can be a product of a chemical reaction, it oftentimes is. And so that's kind of somewhat of a hint. Again, I don't want to make this go too fast. If you look carefully at that test tube, you can see up near the top condensation of water, suggesting strongly that water is indeed one of the products of this chemical reaction.
Kind of smells like burnt marshmallows.
Yeah, and it probably is the result of me burning some of that sugar, but we are accomplishing, again, in general, kind of the transformation that we want. And once again, in addition to that finding of the condensation at the top of the test tube, we're watching that dramatic, unexpected color change as the white solid is transformed into a black solid. And again, that color, black, suggestive of the other primary product of this chemical transformation.
And I'm just gonna harp on a couple words he said. The difference between heating and burning is always an interesting conversation to have during this lab. So in the 2 experiments he's done so far, he's made it very clear that he's adding energy to facilitate the decomposition, which means we're heating it, and then later on we'll see something burned, which makes it a very different chemical reaction.
So then there we kind of have it. I could work with that a little bit more perhaps to make it a little more uniformly black, but that's kind of what we have, the transformation. Again, it's hard to see. If you were here in lab, we'd let that cool and we put it down on a couple of paper towels, perhaps hit it with a hammer, and we get in there and look at that, and we can do that later if we want to. So there you go, reaction number 3. Reaction number 4 is a combination or synthesis reaction where we take a simple substance, in this case a metal, in this case a strip of magnesium metal. Magnesium is what we call an active metal, meaning that it is in general pretty reactive. And we're going to once again use heat to make this reaction go faster, doing this kind of under the fume hood. And you'll see why in just a minute. If I were to leave this piece of magnesium out on the bench for a year, we could accomplish largely the same transformation. But here then the heat allows us to accelerate the rate of the chemical reaction. By exciting those molecules.
Woo!
And it is at this point that it's worth remembering that the air around us consists of a mixture of gases, most notably nitrogen and oxygen. And oxygen plays a super important role in environmental and biological chemistry, because it is a powerful oxidizing agent, which is another broad category of chemical reactions that she'll talk a lot more about, both in the context of inorganic and organic chemistry. If I now then look at this new substance, you can see on my hand there the shiny piece of magnesium that was between the 2 pinchers of the tongs, and here the new substance, which is a very, very different friable white powder. Dramatic color change and dramatic change in the consistency of the substance as a result of that.
And also the evolution of good light.
Yeah, you saw that in the implied heat that it suggests. So again, since how are we doing on time there?
Good. So again,
Everybody
the
loves this.
concept of that being immersed right in the flame versus the heating before.
The metallic properties of luster and malleability and ductility. Into the flame it goes, where we heat up the molecules of atoms of magnesium very fast, break some bonds, produce then the chemical transformation, evidenced by that evolution of a bright light and the dramatic change in the physical properties of the substance after the reaction. Reaction number 6, a single replacement reaction between a metal, again, magnesium, one of our go-to metals for relatively quick chemical reactions, and an acid, in this case hydrochloric acid, again one of our dependable reagents in inorganic chemistry lab. Here the hydrochloric acid going into the test tube, and I'll do this reaction twice to sort of demonstrate what's kind of going on. Here the thermometer probe put into the hydrochloric acid, reading about 23 degrees Celsius. And then what I'm going to do is put in a little bit of magnesium. This magnesium has been ground up really fine. Another thing we can do to accelerate the rate of chemical reaction. Can you see that? And I wish I'd go up a little bit, down a little bit. I don't
You're
know.
good. I got you. I got you.
I'm gonna
Wherever you are, I'll go.
the way here comes the magnesium into the HCl. And so, what are the primary observations you make here? The obvious one is the evolution of that gas. You can see the furious bubbling there as the magnesium and hydrochloric acid react. And the other important observation is you can watch the temperature of the surroundings, the water and the HCl there increase dramatically. WTF on that. It must mean there's been a dramatic rearrangement of the energies of the reactants versus the products. So the two things, the production of the gas, vigorous bubbling, and the dramatic increase in temperature, suggestive of that chemical change. Do that reaction again, only this time I'm going to try and couple it to the seventh reaction, which is a
Sixth
combination,
reaction.
sixth reaction, sorry,
Okay.
combination reaction. This one's much trickier to do on video. You really kind of have to be here and have a lab partner to sort of help you do these things, because I'm going to do the same reaction number 5 between the HCl and the Mg, but then I'm going to provide a little additional energy, maybe. Sweet.
Do we need another barbecue lighter?
Thing was really pumping, huh? To my reaction mixture. So I'll put that one there for the time being. I will disappear for 10 seconds to get another barbecue lighter.
They're all kind of. What? Oh, there we go.
Same reaction. I'm gonna pull this one out of the fume hood. Which one of these was working? That
Make sure
one?
you don't hold on to that. You're gonna burn your fingers.
Yeah, that's why I got a big one. So I can
Okay.
hold it high.
Okay.
Here comes that magnesium ground up into the HCl. You expect to see the same bubbling production of the gas. What I'm going to do then is grab that barbecue lighter and hold the flame over the top of the test tube. So if there is that gas, and that gas is reactive with oxygen, we should be able to see/hear that reaction taking place. In goes the magnesium.
Ooh,
Oh.
nice one.
Probably didn't hear that, but Jen added the important sound effects. There was that pop that you heard, and you actually saw a tiny little fireball form at the top of that test tube when we added that heat to the reaction products
That was a good one.
of the other reaction. And so there we have it, the sort of 6 reactions, number 7 here. Our final one, a double replacement reaction between aqueous solutions of hydrochloric acid again, and our sodium hydroxide, our common laboratory base, as we say. I'm going to start by putting a little bit, 3 or 4 milliliters of our sodium hydroxide in this test tube. And once again, monitor the system temperature. Give it a second for the temperature to sort of stabilize. Can everything be seen there?
Yep, we're good.
Again, room temperature, 23 degrees Celsius. All of these reagents kind of sitting out on the bench top for a while. And now here I'm going to add the solution of hydrochloric acid to the solution of sodium hydroxide. If you look carefully at the reaction mixture, you don't see much. No evolution of a gas, no dramatic color change. But if you look at the thermometer, you can easily see that the temperature is going way up, a fairly startling amount, from 23 to about 38 degrees Celsius. And if you touch the bottom of that test tube, it is warm. So here, although no other indications of chemical change, that energy change, that evolution of heat, telling us that something is going on at that molecular and atomic scale as bonds are broken and new bonds are formed. And the bonds broken, bonds formed thing becomes a familiar theme in talking about the why of chemical reactions, changes in energy as matter goes through its changes.